All right, welcome back. It's been not very long for me. I have no idea how long it's been for you. So let's tackle these free response questions. First up, number 18. A school surveyed 450 of its students and found that 80% eat the provided school lunch. A hypothesis test will be used to determine whether there is convincing statistical evidence, right? So if it's asking for convincing statistical evidence, we're going to use a hypothesis test. Convincing statistical evidence that greater than 75% of students eat the provided school lunch. A. Calculate the test statistic for this hypothesis test. So, test statistic, I'm going to answer part B first. We're dealing with proportions. That's just a sample size. We're dealing with proportions. So this is a z-score because proportions. So then the way we find that test statistic is the way we find a z-score. Actual minus average over standard deviation. In this case, because it's a test statistic, there's some unknowns. Our z-score is going to be the actual, which is the 80%, minus the expected, which is 75%, over. And when we're doing the standard error for proportions for a test like this is when we use the square root of the expected proportion times the complement over the sample size. This is on your formula sheet, and just being able to set it up and recognize it, super important. All right, one down. 19. Revisiting hair lengths. Are there any outliers in the data above? Why or why not? Well, we checked for outliers using the Q3 plus 1.5 times IQR and the Q1 minus 1.5 times IQR. So let's test it the other way, which is mean plus or minus 2 standard deviations. And hang on. All right. When your mom calls, you have to answer the phone, you know? All right, so mean plus or minus 2 standard deviations. So we've got the mean 9.18 plus 2 times 8.91. And then we've got the mean minus 2 times 8.91. This is going to be negative. So obviously, since our minimum is 0, we're going to have no low outliers. This is going to be close to 30. So 9.18 plus 2 times 8.91. Ooh, this one is 27. So our maximum could be a high outlier if we use the mean plus 2 standard deviations. So, something to keep in mind. However, this is probably not a good one to use here because we already decided in our multiple choice that this is not normally distributed. So I would actually say, I'm going to make me do the work too. Let's not use that. It's not normally distributed. So we're going to say Q3 plus 1.5 times IQR. And Q1 minus 1.5 times IQR. And so that's 18.5 plus 1.5 times 16.5. And this is 2 minus 1.5 times 16.5. This is still going to be negative, so it's still a no. And then the 18.5 plus 1.5 times 16.5, oops, 16.5 was 43.25. And so no high outliers either, because that's way above our maximum. Okay, so good to think about. If you removed the maximum value, how would the mean change? Well, if we removed this and we're not changing anything else about our set, the mean is definitely going to go down, maybe only a little bit. The median is going to stay pretty much the same. Yeah, we're going from 41 values down to 40. So our median is going to shift from a value to being between that value and the one right below it. It's entirely possible and honestly likely that the median is going to change a tiny little bit, but not significantly. And then the standard deviation should go down because if we take the value that's furthest away from the end out, everything's going to be a little closer in, right? Everything's a little more clustered together. It's not, maybe not going to go down a ton, but it goes down a bit. Okay. 20. Researchers investigated how the size of a bowl affects how much ice cream people tend to scoop when serving themselves. At an ice cream social, people were randomly given either a 17-ounce or a 34-ounce bowl, both large enough that they would not be filled to capacity. They were then invited to scoop as much ice cream as they liked. Did the bowl size change the selected portion size? Justify your answer at a significance level of 0.05. Big clue here. Justify your answer, and here's a significance level. You better believe you're doing a hypothesis test here. So, let's start with the hypotheses. So our null is going to be, since we're dealing with means, our null is going to be that mu1 is equal to mu2. And our alternative is going to be that mu1 is, I don't know, let's say less than mu2. And so then we used mu's, those are variables, let's define them. So mu1 is average ounces served in smaller bowl. And the mu2 is going to be the average ounces served in larger bowl. Okay. Now, thinking about this, did the bowl size change the selected portion size? A lot of you were thinking, okay, maybe we should set this as a not equal to. Maybe we should do this as a two-tailed test. That's reasonable. I think it would also be reasonable to do this as a single-tailed test since we're thinking that, okay, larger bowl is going to mean larger serving. But either way. But let's do it as a two-tailed since it just says change. After hypotheses, we've got our preconditions. So, always random. Is it random? Yes, they were randomly given. So we can say that the treatments, because this is an experiment, the treatments were randomly assigned. And the treatments here are the bowl size. Small enough? Well, we are sampling without replacement. So 36 and 32, reasonably less than 10% of all people serving themselves ice cream. Okay. And then since this is about means, right? We're dealing with means. This is not big enough. This is normal. So we're always assessing for normality, but for means, we actually just say that we're testing for normal. So 36 and, no, not use the plus sign. And 32 are both larger than 30. So can assume normal, right? This is a two sample test. And so both sample sizes need to be greater than or equal to 30 in order to be working with a normal curve. All right, after hypotheses and preconditions, we have the formula and calculations. Calculate. Okay, so with formula, we always want to put the name. The name of this is a two-sample t-test for a difference in means. And we want to know the probability that t is either greater than a value plus the probability that t is less than the negative version of that same value. And when we do our, when we run our test, we're going to get that t-score. It's just annoying to calculate it by hand. And we know that since it's a not equal to, it's a two-tailed t-test. And so basically this probability right here is going to align with this part of our curve. This probability right here is going to align with this part of our curve. Great. So now let's throw it in the test. We've got, oh, wrong buttons. Two-sample t-test. And our x bar 1 is going to be 5.07. Our standard deviation for 1 is going to be 1.84 because we said that that's the small bowl, right? 1 is the smaller bowl. Make sure those match. Otherwise, you're going to end up sad. You're going to get a really weird p-value and feel like you did everything wrong. And really, you just have it in the wrong direction. The sample size for the small bowls is 36. We're going to do the same thing for sample 2. So that's 6.58 and 2.91 and 32. And then I'm running out of room. We're going to say mu1 is not equal to mu2. Mu2. Right, that matches our alternative. This should always match our alternative. So thankfully, I have not done another test since I did this earlier today. So it's all in there. So we get our t-score of negative 2.52 and our p-value, and I'm always going to write this as a p-value, of 0.015. So first up, I'm going to say that this is 2.52 here and 2.52 there. So we have all of our calculations. Last but not least, we are going to write our conclusion. And we were given a significance level here. How lovely is that? So our conclusion, 2 sentences. Because our p-value of 0.015, you must say the actual p-value, is less than our significance level of alpha equals 0.05. P is low. We're going to reject the hoe. We reject the null hypothesis. That's sentence 1. We rejected the null hypothesis, so we have convincing evidence that, and then here's where we talk about the alternative hypothesis in context, that people do not serve themselves the same amount of ice cream in a small bowl as they do in a cat interference in a larger bowl. hypothesis test done. See, they don't have to take 1,000 years. Just got to knock them out. Okay. 21. Is the situation described in question 20 an experiment or an observational study? We said it's an experiment because we randomly assigned treatments. It's not like the most perfect of experiments, but it's definitely an experiment. We didn't just collect data after the fact. If you get a significant p-value in part D, can you say that having a larger bowl causes people to take more ice cream? Actually, yes. Experiments can establish, I'm going to spell this one carefully, causal, not casual, relationships. Observational studies can only establish associations. Again, study above, fairly weak. We definitely want to repeat that, but it was an experiment. We got a significant p-value. We have a potentially causal relationship. We'd want to replicate this, which is where a lot of studies fall down, is the replication, but still. Okay. Create and interpret a 95% confidence interval for the difference in mean ice cream serving size from the problem above. This, because we did the whole hypothesis test, I'm just going to use my calculator to get the interval. So I'm going to do stat tests, and I'm going to go to 2-samp t interval. So this is a 2-samp t interval. What's nice is it's going to pull all the data from your hypothesis test. So x bar 1 should already be there as 5.07. Standard deviation 1 should already be there as 1.84. N1 should already be there as 36. I'm going to x bar 2 should already be there as 6.58. Standard deviation 2 should already be there as 2.91. And sample size 2 should already be there as 32. Now, the C level, the confidence level, we're going to put as 0.95. We never need to do it pooled, not for this class. So we're going to calculate that and get our interval. So because of the way I plug these in, my interval goes from negative 2.712 to negative 0.3078. So the interpretation part here is we are 95% confident that the interval negative 2.712 to negative 0.3078 contains the true difference in serving size between those with large bowls and those with small bowls. And maybe I should switch the order there because it would be small minus large that gives us negative. Too much. Okay. Large bowls, small bowls. Okay. And no period. Okay. So that's our interval and our interpretation. How does this compare? Okay. This interval has negatives on both ends, right? So it never goes from negative to positive, which means 0 never occurs in this interval. So 0 is not in the interval, right? It's not between the two bounds of the interval. Goes with a significant result at alpha equals 0.05. So because we got a significant result in the hypothesis test, we're not going to have a possibility of zero in this interval. Conversely, if we just have the interval and we see that this is an interval for a difference and it doesn't contain zero, well, great. So we're going to get a significant result. We don't know exactly what that p-value is, but at a 5%, right? 5% goes with 95%. We're going to end up with a significant result. If we're not looking at a difference, if this were just for a single value, it changes from is zero in the interval to is the null in the interval. So there we go. All right, 23. In 1998, as an advertising campaign, the Nabisco company announced a 1,000 chips challenge, claiming that every 18-ounce bags of their Chips Ahoy cookies contained at least 1,000 chocolate chips. Dedicated statistics students at the Air Force Academy, true story, probably also a little bored. Like, let's be honest, this is what you do when you get bored. Purchased some randomly selected bags of cookies and counted the chocolate chips. Okay, to be fair, it's 1998. They also don't have, YouTube or games on their phone or brain rot or whatever. Some of their data are given below. So here's a list of their data. What is the sample mean of this sample of the students' data? All right, this I'm going to put in my list and do some 1var stats. So that is pretty annoying. I'm going to pause the recording so that I don't actually put you to sleep. Okay, pop that in list, did 1var stats, no frequency list, and we get a mean of 1238.1875. Given your answer to part A, set up, perform, and conclude a hypothesis test. Okay. So, our hypotheses. The null is that mu is equal to 1,000. And the alternative is that mu is greater than 1,000. Mu in this case is the average number of chocolate chips in an 18-ounce bag of Chips Ahoy. Preconditions. I'm gonna save some room here. Random. Randomly selected bags of cookies. Problem states randomly selected. And this is not an experiment because we're just collecting data. Small enough. There's 16, or n is 16. So 16 is very reasonably, it's really hard to write with a cat on my hand, very reasonably less than 10% of all bags of Chips Ahoy. Right, we're sampling without replacement, so technically we're changing the probability, but we're changing it by such a tiny amount that we're not worried. Okay, and then it's means. Since we're dealing with means, we're thinking about normal. It does not say anything about the population being normally distributed. Our sample size is 16, which is not greater than 30. So we want to make a dot plot or something to show the distribution of this as normal. I'm going to do that in my calculator. I'm going to say stat plots. So second y equals, turn that on. Actually, I'll do this as a histogram. That's fine. And then I'll do zoom 9. It's not super normal, but it's we get a histogram that looks like this. I would say that's free from strong skew and outliers. Close enough. All right, then we've got our formula and our calculations. Baby, you're causing a ruckus. Okay. Formula and calculate. So this is a one sample t-test for a mean. So stat tests t-test. We're going to use our data this time. So t-test, we're going to use data. Our null hypothesis is that there's 1,000. Our list is, I put the data in list 1. Our frequency list, I'm just going to make that be a 1 because I don't actually want a frequency list. And then our hypothesis is that mu is greater than the null. And so we get the probability that t is greater than 10.11. This is what our distribution looks like. That's our shading. And our t was equal to 10.11. Our p-value is 2.176, which is not possible because there's scientific notation. So it's times 10 to the negative eighth. So remember, this cannot be greater than 1. Oops, I should probably scroll that. This cannot be greater than 1. So if you get a p-value greater than 1, there has to be scientific notation. Now we can conclude our test. So conclusion, and this is all just for part A. Because our p-value of 2.176 times 10 to the negative 8 is less than any reasonable significance level, we reject the null. We have convincing evidence. That's not a word. Convincing evidence that the mean number of chocolate chips per bag is greater than 1,000, right? That was our alternative, that it's greater than 1,000. Okay. A. Oh, no, sorry, that was B. Oh, thank goodness that was B. Given your conclusion in part B, what type of error might you have made, and explain what this means in context? Okay. I'm going to shrink this buddy down. Oh. My cat is throwing things on the floor, and I don't even know why. She got fed, and she has lovely warm places that she could be sleeping. She has toys she could be playing with, but she prefers to throw everything on my desk onto the floor because she is a monster. But that's okay. Okay, so let's see. Given your conclusion in part B, what type of error might you have made? Well, since we rejected the null, we could have incorrectly, we could have gotten a false positive. And so we could have made a type 1 error. What this means in context, we think the average chips per bag is greater than 1,000, when in fact it is not. C. D. Create and interpret a 90% confidence interval for the average number. Again, I have all this data in my calculator already, so I'm just going to go to a T interval. So T interval, the list is still going to be list 1, not I. The frequency is still just going to be 1, and the confidence level, it asks for a 90% confidence. So make sure that our C level is at 0.90 or 0.90. When we do that, we're going to get an interval of 1196.9 to 1279.5. So we are 90% confident that there are between 1190, I'm going to say 7, and 1279.5 chocolate chips in an 18-ounce bag of chips. Ahoy. In 1998. All right. If you wanted to cut your margin of error from part D in half by changing the sample size and keeping all else the same, what new sample size would the students need to use? Okay, so this one is actually a little fun and exciting because it's not just another hypothesis test. I feel like we're getting really good with those now. So for part E, we're changing the sample size. So right now, the actual average, so the sample average, is what we got in part A, this 1238.1875. So 1238.1875. Okay, so I was thinking about this more with proportions when I actually added this to the question, but that's fine. All right, so our confidence interval is always the actual, well, sorry, I shouldn't say that. I should say the sample statistic plus or minus. In this case, the critical value is going to be a T star times the margin of error. Okay. Our sample statistic is the sample mean we got. So 1238.1875 plus or minus critical value. So to find our T star, our critical value for a 90%, we're going to use inverse T. We're going to say our area is 1 minus 0.9, that whole thing divided by 2, because we want that even distribution. So the area is going to end up being 0.05 because that's half of the 10% left. And then our sample size was 16. So our degrees of freedom in this case is just 16 minus 1, is n minus 1. So it's going to be 15. And so we're going to get our critical value. And again, we can ignore the negative because that's taken care of by this plus or minus. 1.753 times our, or excuse me, not our margin of error up here. This should be our standard error. This whole thing is our margin of error. Okay, so right now we have our standard error. It was going to be the standard deviation, which we can get from our 1-var stats. It'll all still be in there. And it's a sample standard deviation of 94.282 divided by the square root of 16. That's just how we find our sample standard deviation. So we want this part to be half as big. So let's figure out what it is to begin with. We've got 1.753 times 94.282 divided by root 16, which is just 4. So right now, the margin of error is equal to 41.319. We could have also gotten this by finding the difference here and dividing by 2, but whatever. So that's currently our margin of error. We want to divide that in half. So we want a margin of error equal to 20.6595. So then we're changing our sample size. So we're going to just set this part up. 1.753 times 94.282 all over root of n to equal 20.6595. So then we're just going to algebra. Divide both sides by this. 1.753. So we get 94.282 over root n is equal to 11.78525. And we don't actually need these parentheses anymore. These are going to switch places. So we're going to get 94.282 just because when we multiply by the denominator and divide to isolate, 0.78525 equal root of n. Then we're going to square both sides to undo that. And so we have... Oh, I don't have that here. So 94.282 divided by that 11.785. That's just 8. So 64 is equal to n. So notice, we wanted to cut our margin of error in half. We wanted to divide the margin of error by 2, which meant we needed to increase our sample size by 2 squared because of this square root. So we needed to increase our sample size by a factor of 4 because 16 times 4 is 64. You could probably have figured that out algebraically, but still good to go through the math sometimes. All right, moving right along. 24. The manufacturer of a metal stand for home TV sets must be sure that its product will not fail under the weight of the TV. Because some larger sets weigh nearly 300 pounds, the company's safety inspectors have set a standard of ensuring that the stands can support an average of over 500 pounds. Belts and suspenders. Their inspectors regularly subject a random sample of the stands to increasing weight until they fail. They test the hypothesis that the average weight they fail at is 500 against the alternative that the average weight they fail at is greater than 500, using the level of significance of alpha equals 0.01. Again, higher stakes, lower significance levels. If the sample of sands fails to pass this safety test, the inspectors will not certify the product for sale to the general public. Okay. So is this an upper tail or lower tail test? And then in the context of this problem, why do you think this is important? So for A, this is an upper tail because we don't care about stands being too strong. We want to know that it's at least it can handle at least 500 pounds. Right? So we're interested if we think the null is here at 500 pounds, we want to know the probability that if this is true, we're here or higher, right? We don't really care about it being less because that's going to fail. That's not ideal. Part B, explain what will happen if the inspectors commit a type 1 error. So a type 1 error is false positive. So they reject the null and think they have stands that can support over 500 lbs. But in reality, they don't. So that is describing the type 1 error. The consequence of that, stands may break. And TVs may fall on people. That doesn't sound ideal. A type 2 error is they fail to reject the null. When they should. The inspectors think stands are not able to support over 500 pounds. When in reality, they can. So that's the description. The consequence of this is that product is not certified. When it could be. Right? So then E, nope, that's not letters. D. Which type of error is more consequential? I'm going to say a type 1 because missing out on some profit is not as important to me as hurting people by crushing them with televisions. Type 1. People over profit. Okay. Almost. Mr. Math knows that the faster you run, this is super similar to the one we did together. Faster you run, the faster your heart rate, the higher your heart rate will be. He wants to create a linear regression line for his data. He sets his treadmill to a speed in miles per hour and then records his heart rate in BPM after 30 seconds at that speed. The data is shown in the scatter plot and regression analysis below. Write the equation of the least squares regression line. Y hat is equal to these guys. 60.05. That's our constant. So it does not have the x, plus 12.35x. We're going to say y is the BPM and x is the walking speed. Done. Interpret the slope and y-intercept in the context of this problem. So the slope for each additional mile per hour of walking speed, BPM is, and this is a key word, predicted to increase by about 12.35. Boom, slope. Y-intercept does have meaning in context, so at 0 mph walking speed, so basically you're still. BPM is predicted, again, to be 60.05. Now, we want a 98% confidence interval for the slope parameter. So that's when we're going to use our standard deviation and our speed, or standard error and our speed. I swear, cat, if you throw my headphones into a ditch, no more chicken. Never again. Assume that conditions for inference are satisfied. That's great. I'm just going to go straight to the interval here. So, we need our slope plus or minus our t star times our standard error. Our slope is 12.35 plus or minus our t star. So t star, we've got 98% confident. And our sample size is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So our n is 10. We're going to do inverse t. The area is going to be 1 minus sea level. Make sure you put that in parentheses if you're throwing it all in at once. Over 2. The degrees of freedom is going to be 10 minus 2 because this is 2 variable, x and y. When we do that, we get 0.01 as our area, because 98% confidence, and degrees of freedom should be 8. And so we get t star equals, again, we can ignore the negative because the critical value gets plus or minus anyway, 2.896. 0.896 times standard error. This is the nice part. We have that 0.382. So if we do 12.35 minus 2.896 times 0.382, we get 11.244. If we change it up and do plus instead, we get 13.456. Cool. So there's our interval. Compute this interval and interpret it in the context of this problem. So, interpret it. We are 98% confident that for each additional mile per hour of walking speed, the interval 11.244 to 13.456 BPM. Let's add the BPM there. Sorry, my handwriting is trash right now because my contacts want to die. BPM to 13.456 BPM contains the increase in BPM, or contains the true slope. So we'll say average. Okay. All right. Let's take a little pause there. Oh, I see. Because then the last question is a different document. So I'm going to pause. I'll set that up, and I'll see you in a moment. It will feel like no time at all. Okay, last but not least, our chi-square question. You definitely need to know how to do this. Okay. Hello. So the behavioral risk factor surveillance system is an ongoing health survey system that tracks health conditions and risk behaviors in the United States. Cool. In one of their studies, a random sample of 8,866 adults answered the question, do you consume 5 or more servings of fruit and vegetables per day? The data are summarized by response and by age group in the frequency table below. Okay, so 1, we've got our data in a table. 2, we have a random sample, a single random sample. Good things to keep in mind. Do the data provide convincing statistical evidence that there is an association between age group and whether or not a person consumes 5 or more servings of fruits and vegetables per day for adults in the United States? Okay, so this to me sounds like this is a chi-square test for independence. So some ways I know that. It's independence because we have a single group, a random sample, and 2 variables. Yes or no. So, fruit consumption and age group. So we're trying to see if fruit consumption and age group are associated or independent. So that's 1 group, 2 variables. That's independence. Now we have to actually perform the test. So it's a hypothesis test. We're going to start with the hypotheses. These ones we can write out in words. So the null hypothesis is that fruit and vegetable consumption is independent. I'm going to type this. I don't know why I haven't been doing that. It's not been working very well in Notability, but I think it'll work fine here. So the null hypothesis is that fruit and veg consumption is independent of age group for adults in the United States, which means our alternative, can I make this smaller? Whatever. Our alternative hypothesis is that it's not independent. So alternative, I'll add the A later, is that fruit and veg consumption is not independent of age group for adults in the United States. Okay, cool. And just before I forget, this is our alternative. There we go. All right, so there's our hypotheses. We didn't use any variables, so we don't need to define them. That's how you know. Okay, whatever. Next, we've got our preconditions. So, we're going to check, is it random? A random sample. So, problem states random sample. And we need to check that the expected count. So this is our big enough. So the expected counts all greater than or equal to 5. So I'm going to recreate this table up here, but I'm going to say that it's our expected counts table. So we've got age group, 18 to 34, 35 to 54, and 55 plus. And then we've got yes, no, here's our total, and here's our totals. And so then I'm going to do these expected counts by hand just because we haven't done that a ton. In a lot of cases, in this question, it would be very boring if we just stopped at the preconditions. That would be pretty unlikely for the College Board. So I have been just going forward with the test and then filling this in after my matrix is done. Because the calculator makes that expected values matrix for you. So I'm going to put my totals in. 6675, 8866, and then we have 972, 2911, and 4983. Okay. So again, can I zoom on this? I wonder. Nope. Less helpful. Okay. So expected count is row total times column total over total total. So for this particular box, I'll just do that up here and then I'll just fill the rest in. So row total is 972 times column total 2191 all over total total 8866. And when you do that, you get about 240.2. We do the rest of that and get 731.8. And again, it's totally fine that these have decimals, even though that's not a possible amount of a person. This is just what we're expecting. Expected values are fine as decimals. Don't round. 1.4 and 719.4. So all expected counts are greater than 5, so it's big enough. We're sampling without replacement, but again, we're more than clear on the small enough count because we're taking even 9,000 adults from the United States is a drop in the bucket. There's 340 million people, more than that. I don't know. Keeps growing. Great. So we've met our preconditions. After preconditions, formula, and calculations. So we've got, this is a chi-square test for independence. So we have our name. And then we have to calculate our test statistic and p-value. So I'm just going to check the scoring guide real quick. So step 3, we have to correctly calculate the two components, and it doesn't say. Yeah, that's fine. We're going to pop this in our matrix. Don't feel like doing this by hand. So chi-square test for independence, and we're going to calculate our chi-square test statistic, which is the sum of the observed minus expected squared all over the expected. We could do this by hand. It's not that deep. Well, this is our expected counts, and we have our observed counts, but let's just throw it in a matrix. So I'm going to say second matrix. I'm going to go over and edit. This is a 3x2. And I'm putting all of my observed in matrix A. Observed in matrix A. So we've got 231 and 741 and 669 and 2242 and 1291 and 3692. And remember, the matrix you're putting into your calculator is only the actual values. You don't include any of the totals. So that's why I said it's a 3x2. Okay. So then we're going to do our chi-square test. And since it's an independence test, not a goodness of fit, it's just chi-square test. Observed in matrix A. Expected, you want to put in an empty matrix right now. Expected. I'm going to put in empty in numbers. And empty, you could also use values from your big enough check. And then you're going to calculate. Then we write down what we've got. So we've got our chi-square test statistic, which is 8.983. Our p-value is 0.0112. And our degrees of freedom is 2. And that's 2 because we have a 2 by 3. And remember, degrees of freedom are rows, number of rows minus 1 times number of columns minus 1. So when we have this chi-square test for homogeneity or independence, it's always, oh, you can't see that. Got to scroll a little. Hello, wakey wakey. Yeah, there we go. Sorry. Did not realize it was not showing you that. So this is basically all just matrix stuff. You plug it in. There you go. Now we write our conclusion. So it's always because they're p-value. And we were given a significance level, weren't we? Oh, we were not. So 0.01 is pretty small. So because our p-value of 0.0112 is very small, is less than a significance level of alpha equals 0.05. And maybe we go up here and say, there's not giving us a significance level, so we're going to say significance is alpha equals 0.05, right? Oh, I put that up above where you can see. Hello. Oh, why is this being so dumb? Okay. There we go. So I just said significance is 0.05 because I got 0.011. So we don't quite hit any reasonable significance level. So I'm just going to define one. Significance level is 0.5. We reject the null hypothesis. We have convincing evidence that there is an association between age group and eating, what is it, 5 or more servings? 5 or more servings of fruit and veg per day for adults in the United States. And you really want to get all those pieces in the context, right? We really want all the pieces and parts. Okay, cool. I hope that was helpful. I hope you are having a nice time studying and also getting some sleep in the meantime. Come here. Come here. I'm going to try and get the other cat for you. Come here. She's being all squirrely and weird. I don't think we get a second cat. I'll try one more thing. No dice. It's time for her second dinner, and she will have none of the socializing. Good night. Where's my mouse?